In this video, we're going to take a look at the next calculus calculation that is related to these polar curves. And we're going to look at area, right? So we've already done slope. We're going to take a look at area. And we're just going to look at the basic area problem, not the more complicated regions that we may have studied in terms of implicit functions. But for these polar functions in terms of r and theta, we want to be able to find the area of certain regions. So let's go ahead and actually make this problem a little bit more well-defined. And whenever you hear someone, particularly in math, say something, well, let's make it well-defined, is we want to make it clear, right, what type of problem we're solving, or what is the problem we're solving and what we're not solving, and like what are the parameters, right? So to make sure that we have a procedure that will always work as long as we carry out that procedure correctly. So let's start with a sketch, as we often do. And so let's say this is a ray, right? And remember, a ray starts from a well-defined point, and then it emanates indefinitely in one direction. And let's say that this ray corresponds to an angle. Now, I'm not going to draw the angle here. I don't want too much stuff on this sketch, but this corresponds to an angle of theta equals, let's say, alpha, right? I like alpha. And then let's say that there's another ray like this. And let's say this one corresponds to an angle, again, measured from the positive horizontal, but now this one stops in the second quadrant, and that corresponds to theta equals, let's say beta, alpha and beta, we like that. And then let's say our polar curve now looks from this. So when theta is equal to alpha, we have, let's say we have a radius at this point, and then our curve is nice, continuous, and the radius changes, and then when theta is equal to beta, it has this radius, and there we go. So this is our polar curve, which has the standard equation r equals f of theta. And then the region now that we're referring to is this thingamajig right here that I'm shading in blue. And notice how I'm doing it. It's almost like I'm drawing these a few extra rays starting at, and I started at alpha, theta equals alpha, and then I went counterclockwise until I got to theta equals beta, and then I stopped. So it's basically the region that is between these two rays and this polar curve, right? So we're not talking about vertical and horizontal axes now. We're talking about these, I guess you could call them radial axes, and then our polar curve is essentially that third boundary, right? So our goal is to figure out the area in blue, all right? Now, because of the nature of these polar curves, and many of them are periodic, you keep going around, and you could just be tracing out the same area over and over. You don't want to double or triple or multiply count the area. So we have to set some, for lack of a better word, boundaries on alpha and beta. So basically, we don't want to go more than a full revolution. So alpha is essentially going to be our smallest value of theta. And then it's, again, to have a non-zero area, these two rays have to be different. So they can't be the same. So they're going to be like this. So alpha is going to be less than beta, but beta can't be too big. The most it can be is alpha plus 2 pi. In other words, we don't want to go more than one full revolution in our coordinate system, because if we do that, then we run the risk of double counting or counting the same area, or measuring, I should say, where we don't count area, but measuring that the area multiple times, right? So this is a key requirement here. So let me just put a little bullet there. And then the next requirement is just for simplicity, that f of theta is continuous for all values of theta going from alpha to beta. So we want that f of theta to be continuous like this. So be continuous for theta that is between alpha and beta, right? So we want continuity, and we want basically our range, right, going from alpha to beta to be no more than 2 pi units. All right, so how are we going to find this, right? What is the procedure? Well, as you might guess, it's going to involve a definite integral, but it's not going to look quite the same as the previous definite integrals that we've used to compute area, right? Why is there a difference? Well, if you think about it, that procedure for finding area was based on using rectangles, right? So we started with our Riemann approximations. We used rectangles, and then we got this really nice, simple definite integral where you basically just integrate the function from a certain x value to another x value, and then you were done. But looking at this region here, it doesn't seem like rectangles would be a good way to approximate this area in blue. So the question is, what could we use? What other geometric figure could we use to approximate the area of a region that would look like this, right? So you're still going to break it up. In fact, I've already broken it up. In fact, I could do something like this. Let me just draw these out and extend them until they touch that polar curve, right? So let me just do like this. And imagine, it looks like a weird pizza. It's like a pizza where the crust doesn't form a nice circle. So it's like you have these little wedges, or call them pizza slices, and we would take out each of these things, each of these slices of the pizza, the irregularly shaped pizza, figure out the area of each of the slices, sorry, gotta watch my grammar there, and then put them back together, piece them, add them up, and then get an approximation for the total thing, right? So let's kind of take out one of the slices and ask ourselves, well, what would be a good figure to kind of represent this? So I'm going to draw one. I'm just going to draw one of them on the on this region right here, and then I'm going to take it out and do it as a separate sketch. You'll see what I mean. So this reminds me of, so for instance, suppose we now pretend that the boundary is actually circular. Now, if it's a circle, then it has to have a certain radius. So I'm going to pick a radius anywhere between this smaller radius and this larger radius. So I'm going to pick anything, any radius, any of these here, and just put a point. And then what I'm going to do is draw an arc, a circular arc now, which actually that doesn't look like a circle at all. What am I thinking? So more like this. Yeah, there we go. That's a little bit better. So that circular arc, and this, you notice here, I would have to extend it a little bit. So I'm gonna extend that one, and then I'm gonna take all of this, and that's now my perfect pizza slice. I'm going to take it over here and just draw it a little bit bigger. And then so let's take this slice of pizza. We can't eat it. I'm kind of hungry. I wish we could eat it. I'm just going to put it under the microscope and blow it up. So it looks like this. Now, again, being really stingy, right? I'm going to give my friends really small slices of pizza. So the angle here is going to be pretty small. I'm going to call that, because delta represents really small things. So I'm going to call this little angle here delta theta, really small, right? And then of course that radius that we picked, to form the boundary of our slice of pizza, right? This radius right here, let's just call it R, right? In fact, it is, R, it's a radius. And then the question is, do we have or do we know a formula that will give us the area of this? This figure is called a sector, right? What is the area of a sector? Well, if the angle is measured in radians, which is another reason why we love radians, the formula for the area of a sector is pretty easy. So I'm just going to say the area of this particular sector is equal to, it's 1/2 times the radius squared. You got to square your radius, and then times the angle, which in this case is delta theta, that really small angle, right? Because I'm stingy with my pizza. So if I want the area, or now if I want, so let me actually let me do this. Let me put area of sector just for a little s there, right? So this is the area of that one sector. Now I would do the same thing for each of the remaining irregularly shaped slices of pizza. So I would repeat this process, just like how we repeated the Riemann process with a whole bunch of rectangles. I would I'm taking basically a page from Riemann's book, but I have to convert it and use this formula instead of the formula for a rectangle. So then I could say the area of all, now my blue area is approximately, so the area in blue is, in fact, let me put the blue right there. Oh, so the area in blue is approximately the sum of all of these. So how does this work? Well, again, let me just kind of introduce or remind you of some of the notation that we use. So, when we pick that specific radius, that radius will change based on where we are in the polar coordinate system and what part of the curve we're using. So that will have a specific value that could possibly change. And also, our delta could possibly change. It could be a constant delta in terms of how small, but maybe I like some of my friends a little bit better than others, so I might give them a slightly bigger piece of the pie, and some people might get a smaller piece. So the delta will change. So I'm going to say that as well. So then I would add up all of these going from the first k, which would give me that first little wedge right there, all the way to the last. So here's our, again, it's a Riemann approximation, but now for a polar curve, k going from 1 to n, and it's 1/2 times the radius squared, or each radius squared, times delta of theta sub k, right? So now I'm going to switch back and say, well, how do we go from an approximation to the actual area? We take a limit. So we said, what happens to this sum if our delta gets really, really small, right? So if we're using a uniform delta, we could say, oh, what happens when n goes to infinity? If we're not using a uniform delta, meaning the delta isn't the same throughout the approximation, saying that n goes to infinity is not sufficient to guarantee what we want. So there's some deeper math stuff going on there. But here's what we can say. Here's our formula for or polar area. So I'm going to write down the limit definition. So it's the limit as our delta approaches 0. And I'm just using this as the abbreviation for delta of theta, so k, of our Riemann approximation that looks like this. Right, and we got that, and then delta theta sub k. But we know what happens when under certain conditions, right? And continuity is a really strong condition that guarantees nice stuff will happen when we take limits of Riemann sums. That's where we get a definite integral. So all of this now gets replaced with an integral sign. And in this case, our approximation started at theta equals alpha, and then ends at theta equals beta. That's good. So we got our limits there. We have the 1/2, which is a part of the formula. And then it's the radius squared, so it's r squared. And then we know the deltas, those differences become differentials. So this is d theta. I just realized right here that my theta doesn't look like a theta. I better fix that, right? So there we go. That looks like a theta. And here is our formula for the area as defined previously of a region bounded by polar curves. And if you wanted to, you could go even a step further and say this is the definite integral from alpha to beta of 1/2, and then just replace r with the f of theta. So f of theta, and it's that quantity squared d theta. All right. So again, I didn't want to just write this formula down. I could have certainly just written it down, but I wanted to give you a sense of where this formula comes from. I always like to do that. I mean, math does not just come out of thin air. I think the math is there, and it's there to be discovered, and really cool and clever people figured out a lot of this stuff, right? And I do like the fact also that in explaining where the formula comes from, we have to recall a useful result for the area of a circular sector, a sector. All right, so let's do an example to see how this works, and this will be pretty straightforward. This is the type of example that you'll see in this type of course. And I'm actually going to start with a sketch right now. I am no Maple, I am no Desmos or GeoGebra or anything, but I can draw some of the simple polar curves. I'm going to draw this one that kind of looks like a heart, like that, but it kind of turns sideways. And one equation that could give me something like this is r equals 1 plus cosine theta. Actually, 1 minus. Let's do 1 minus. That will give us this one here. So 1 minus cosine of theta, right? And then let me shade the region that we're going to try to find the area of. Now we could try to find the area of this, this complete heart. As I said, it could be a heart, and the area could be used as a measure of the love you have for something. But let's say our love only occupies that part of the region, right? So in this case, notice this region here. Well, let me just say this. This function has period 2 pi, but our region doesn't cover the entire coordinate plane going from theta equals 0 to theta equals 2 pi. It's only in the first quadrant. So in that case, our theta, think about the standard way of measuring angles in the first quadrant. They have to be between 0 and pi over 2. So that will be, so based on this sketch, right, we can say this, or the problem could simply leave out the sketch, just give you the polar equation, give you the range, right, which will end up being your limits as usual, and then ask you to find the area. So that's what we're going to do with this. So we're going to find the area in blue. All right, well, let's set it up and see how we can do this. So we're going to integrate from 0 to pi over 2, and let's apply our formula. It's 1/2 times whatever the radius is, that quantity squared. So I'm actually going to use some square brackets here just temporarily, so that we're very, very clear on the order of operations, right? So that's the setup. Now let's execute this thing. So we can factor out the 1/2 for sure, right? And that can always happen in a area calculation in the polar space, because the 1/2 is always a part of the formula. Now, if we FOIL this out, right? Remember to do your first, outer, inner, last thing, and do some algebra. This is obviously a perfect square. When you expand it, you're going to get 1 minus 2 cosine of theta plus cosine squared theta d theta. All right, so just some foiling there. And now when we look at the first two terms, we're happy because, yep, we know how to integrate these. And remember, we're integrating with respect to theta now, no more x. This one, however, is a even power of cosine. And we know for those, we have to use our, I guess you could say, either half or double angle identity, whatever makes you happy. So we're going to use that identity here. It's been a while since we've used that identity, but once again, those trig identities are useful. So cosine squared is it can be written as 1/2 the quantity 1 plus cosine of 2 theta. So like that, d theta. Now let's see if we can clean this up and integrate it. So it's going to be 1/2 integral from 0 to pi over 2 of 1 minus 2 cosine theta, and then distribute the 1/2. So I'll have plus 1/2 plus another 1/2, but now this is times cosine of 2 theta d theta. All right. Well, now when I look at this, I can integrate all of these terms, right? That's not hard. One thing I will do is there are two constants in my integrand, right? The 1 plus 1/2. Well, let's just combine that into 3/2. I think that would be a good idea, so that we'll have one less term to worry about, right? So this is 3/2, and then I have the minus 2 cosine of theta, and then plus 1/2 cosine of 2 theta d theta. Okay, and now let's write down our antiderivative, right? Don't forget the 1/2. So I'm going to put the antiderivative in square brackets. So here we will have 3 over 2 theta, because theta is now my variable. And then this will give me minus 2 sine theta, because the antiderivative of cosine is sine. And then here, very similar, but we have to divide by the 2. That's the coefficient of the theta. So we'll end up having plus 1/4 sine of 2 theta. And of course the d theta goes away. Don't need a plus c since this is a definite integral. And we're going to go from 0 to pi over 2. And then we apply the last step of our fundamental theorem. Now you can distribute the 1/2 now or after. I'm just going to do it after, right? So at the upper limit, which will be in parentheses, we will have 3/2 times pi over 2 minus, now the sine of pi over 2 is 1. You can double check that. I'll just write the value in. And then 2 times 1 plus 1/4, and then the sine of, now we first have to double this. So when I double pi over 2, I get pi. The sine of pi is 0, so I'm going to put that in there. And then minus, and at the lower limit of 0, now all these terms evaluate to 0 because the sine of 0 is 0. So I'm just going to put there that just as a reminder, and there we go. So what do we have? We have 1/2, and then in the parentheses, I have 3 pi over 4. So we got 3 pi over 4 there, and then minus 2. And I think that's it. And then finally, let's distribute the 1/2. And we will have 3 pi over 8 minus 1/2 times 2 is 1. And then this would be square units. All right. So there you go. Once we have the formula for the area of these polar regions, then yeah, we just kind of go through and whatever integration technique is needed, then we actually apply. So in this case, because there's a trig function involved that was being squared, then we had to use our double angle identity. If it was an exponential function or a quadratic function or something like that, then you'd have to FOIL out, and I think the integration would be a little bit easier there. With that being said, that wraps up this video. So and now we have a procedure for finding the area of these polar curves. I hope you found this interesting and useful and, dare I say, fun. I know I had fun presenting it to you, and I can't wait to present the next topic. So I'll see you in that video.